Hi everyone, welcome to my new video in the Mathematics Essentials series. This video is about how the unit circle definition of trigonometric functions preserves our more familiar right-angled triangle ratios that we associate with these trigonometric functions. Sine of theta equal to the opposite over the hypotenuse. Cosine of theta equal to the adjacent over the hypotenuse. And the tangent of theta equal to the opposite over the adjacent. By the way, a handy mnemonic device to remember these is this. So, ka, tawa. That's what a lot of people say. So that helps you remember that sine is equal to opposite over hypotenuse, cos is equal to the adjacent over the hypotenuse, and tan is equal to the length of the opposite side over the adjacent side. But I actually don't say soka toa, okay? I say soka toa. And the reason I say soka toa is because saying soka toa makes me think of toes when I say toa, and I don't want to think about toes. So I say soka toa. But if you want to think about toes, feel free to say soka toa. Anyways, let's get to explaining things. I'm going to draw a unit circle. And draw a Cartesian plane, an xy plane. There's our y-axis. Here's our x-axis. And recall that being a unit circle, it has a radius of 1. So if I have the origin here and I draw a line to any point on the circumference of the unit circle, I'm going to get, keep that in gray, I'm going to get a line that has a length of 1. Okay? Now, this blue point here, we can just call it point B, in case I want to refer to the origin as point A. All right, and we know that it's going to have some x and y components that form the coordinates of the point B. All right, we know that by drawing this line, sorry, I went to cough. There we go. We know that by drawing this line, we will define an angle theta measured anti-clockwise from the positive x-axis. Okay, and then we can define the cosine of theta as being equal to x, the sine of theta as being equal to y, and the tangent of theta as being equal to the sine of theta over the cosine of theta, which just boils down to saying y divided by x. Okay? So, how do these unit circle definitions of these trigonometric functions respect and do no violence to these three trigonometric functions that characterize relationships in right-angled triangles? Okay, they are the same trigonometric functions, and we want them to be preserved. And one way to make sure that our unit circle definitions preserve these three is to show that these three here follow from our unit circle definition. Okay? So that, okay, if these three are a consequence of these definitions, okay, then these three must be preserved. Okay? So let's do that. What we can do on the unit circle is define a triangle. It's pretty much already defined because we can just drop a vertical line from the point B down to the x-axis. And as soon as we do that, we've got a right angle triangle. Okay, so it's a right angle triangle. All right, and since we have an angle theta, it makes sense to talk about this side being the opposite side to theta, all right, and this side being the adjacent side to theta. But notice that the opposite side to theta, its side length is going to be whatever the y component in our coordinate for the point B is, because this length here, okay, if we just tracked across to the y-axis, wherever we would intersect the y-axis here, this value here is going to be the length of the opposite side. Okay, so some line that we draw from the origin up to that y value is going to have the same length as this side. Okay, even though I did not draw things perfectly, I'm sure that that's intuitively clear. All right, so I'll just get rid of these. And a similar kind of thing is going to hold for the adjacent side. Wherever this line intersects the x-axis, that's going to be the length of the adjacent side. So whatever that x value is, that will be the length of the adjacent side. So the opposite side, we can treat, keep things in gray, we can treat as being equal to x, right? The adjacent side, we can treat as being equal to y. Now what about the hypotenuse? This here would be the hypotenuse, but the hypotenuse we know will be 1 because that hypotenuse is just the radius of the unit circle. Okay, so the length of the hypotenuse would be 1. The length of the opposite side to theta is x, length of the adjacent side to theta is y, and the length of the hypotenuse of that right angle triangle is 1. Now, our unit circle definition of cosine of theta tells us that it's equal to x, and if we divide x by 1, that makes no difference. That's still going to be equal to x. But notice that x is equal to the opposite side, right? And 1 is equal to the length of the hypotenuse. So we could really just replace x with adjacent and 1 with hypotenuse. And we have the more familiar way of thinking of cosine of theta in relation to right angle triangles. A structurally similar thing will happen with the cosine of theta. It's structurally identical. It's just that we're talking about sine of theta instead of the cosine of theta. Well, our unit circle definition tells us that this is equal to y, but we know that y is equal, just as the length of that adjacent side of the right angle triangle we inscribed inside the unit circle, and dividing by 1 does nothing to y. It leaves it untouched. It's still just y. Okay, so we can really replace y with the opposite, and we know that 1 is the length of the hypotenuse, so we can substitute h for 1, and guess what? We've got sine of theta equal to the opposite side length over the length of the hypotenuse, which respects this here. Okay, now the tangent of theta. What about that one? Well, we know that tan of theta is just equal to sine of theta over the cosine of theta. But look, we know that our definition for sine of theta respects this. We know that our definition for the for the cosine of theta respects that. Our unit circle definitions respect our right angle triangle definitions, or they preserve them. Okay, so I could substitute, y for sine of theta here and x for cosine of theta here, and all I would do is go through everything I just did with sine of theta over here and cosine of theta over here, right? But so that I don't repeat that, I'm just going to jump straight ahead to these, and what that would look like is this: the sine of theta being the opposite over the hypotenuse, and the cosine of theta being the adjacent side over the hypotenuse. Remember, we know that the opposite side is just y and the adjacent side is just x, and that the hypotenuse is just 1. And we also know that dividing by a fraction is the same as multiplying by the reciprocal. So let's do that. Okay, the reciprocal of adjacent over h is just h over adjacent. All right, and now you can see that the h variables will cancel, and we'll just be left with opposite over adjacent, which is what this says. Okay, so our unit circle definitions of these three trigonometric functions respect, in other words, they do no violence to these definitions here. Okay, now you might be worried that since we are talking about the unit circle, we always know that the hypotenuse is 1. Okay, so you might worry that these unit circle definitions don't always respect the right angle triangle definitions when we are talking about triangles that have a hypotenuse greater than 1. Well, those cases just refer to scaling the triangle by some constant. Okay, so when you scale a triangle and make it bigger, all right, you know that the size of the angles remain the same, right? And although the side lengths of the triangle change, the ratios between the side length of the triangle don't change. Okay, so that just means we could still express the cosine of theta as the adjacent over the hypotenuse, or the sine of theta as the opposite over the hypotenuse, etc. It's just that the hypotenuse isn't going to equal 1. Okay, so in that case, the cosine of theta, let's imagine if the hypotenuse was like 3, the cosine of theta would end up being something like, x over 3. All right, so it wouldn't equal x, but the thing is, the cosine of theta would equal the x coordinate for some point out here because we've just scaled the triangle. Okay, so it would equal the x coordinate of, the cosine of theta would equal the x coordinate of this point B down here, that blue blob, okay, but it would be the x coordinate for a triangle that's 3 times as big. So imagine we scaled the triangle to make it 3 times as big. We would get a triangle like that, and the cosine of theta would be an x coordinate for whatever that point is, and the sine of theta would be the y coordinate for this point here. Okay, so it's not really going to do any violence. Okay, one other way of understanding this is that you can just think of right angle triangles as just halves of rectangles, so rectangles that have been cut in half, right? And notice that this is 90 degrees, and this angle here is 90 degrees. This angle here is 90 degrees. Okay, this angle will be something like theta, that we might call theta, and this angle we might call phi. Okay, if this was a square, theta and phi would both equal 45 degrees, and their sum would be 90. Okay, but we don't know that they're 45. Well, if it's a rectangle that isn't a square, we know they aren't 45 degrees, but their sums must equal 90 degrees. Okay, notice if we just made this rectangle bigger. So imagine that this is just a rectangle that we've blown up. Okay, so we've rescaled it by some constant. So if this was like the length of this rectangle, and this was the width of this rectangle, let's say we made this rectangle 5 times as big. So this would be 5 times the width of our previous rectangle, and this would be 5 times the length. Right, and this would be 5 times the width of our previous rectangle. Notice that the size of the angles wouldn't change. These interior angles would all still be 90. Okay, if we drew a line from corner to corner, this angle here would still be, did I call this one theta or phi? Yeah, this one would still be theta. All right, this one here would still be whatever phi happened to be. Okay, so if you can see that scaling the rectangle makes no difference, right? And rectangles are just 2 triangles slammed together along their hypotenuse and flipped around. Slamming this triangle into this triangle, so just joining them together in order to get a rectangle. Okay, then you can see that scaling a rectangle makes no difference. Okay, and the ratios between the sides of this triangle that's been scaled and our previous one here, notice the ratio of the width to the length would just be whatever W is over L, right? And similarly for this scaled up rectangle, it would just be whatever the width is, which is 5W, over whatever the length is, which is 5L, okay, and the 5's would cancel, and we'd just be left with W over L. So you can see the ratios don't change in a rectangle, and rectangles are just two right-angle triangles slammed together in the right way. So if it doesn't change for the whole thing, right, if the geometric relations don't change for the whole thing, the geometric relations mustn't change for parts of the whole thing. In other words, the two triangles, right? So I hope that alleviates any worries about scenarios in which you are dealing with a hypothesis that's not, not a hypothesis, a hypotenuse that's not equal to 1. All right, if you found this video enjoyable or helpful, please give it a like, and if you want to, you can share it with some friends. If you'd like a notification when I upload another video, subscribe to my channel. Bye for now.